here in Chapter 13, and specifically limits that deal with sequences in series. Talk about mostly infinite limits and some tricks and strategies on how to calculate those particular limits. So let's take an example here. First of all, the limit as n approaches infinity of 10 times 1/2 to the n. So intuition here, we're just going to kind of see as n goes to infinity. So that means as n gets larger and larger and larger, as n grows without bound, okay, it's going to keep getting bigger and bigger and bigger. So let's look at our first term. First term, when n equals 1, we get 10 times 1/2, which is 5. Second term, we get 10 times 1/2 squared, which is 10 times 1/4, which is 5/2. And that should make sense because we're multiplying by a half, right? So we're going to get smaller and smaller each time. The third term would be 5/4, and then 5/8, and then 5/16, so on and so forth. Hopefully what you're noticing here, 5/32, 5/64, is that each term is half as big as a previous term. Okay, but think about it. Will this ever actually get to 0? We're taking half and a half and a half, so 5/32, 5/64, 5/128, 5/256, 5/512, 5/1024. It's tiny, but it's not 0. So the limit as n approaches infinity, notice that I not say when n gets to infinity. N will never get to infinity. And since n can't get to infinity, we will always be taking half of something, which means we'll always have something remaining. So our limit as n approaches infinity is equal to 0. Okay, be careful with what that means. If n could get to infinity, then 10 times 1/2 to the n would get to 0. But since n can't get there, 10 times 1/2 to the n won't get to 0. Okay, but we still say the limit, okay, the absolute smallest it will ever possibly even consider getting is 0. So a limit is really what would the value get to if it could get there. Okay, so it's kind of sounds weird. It's a little abstract. Let's look at a graph of that. And this is what's happening, and maybe this will make a little more sense. So we had 5 was our first term, and then we went down to 5/2 as our second term, and then 5/4 as our third term, and then 5/8. I'm just cutting these in half as I go here. 5/16. Right, notice what's happening. We're going to keep getting closer and closer and closer to 0. It is asymptotic at 0. Okay, it will run along 0, but it will never get to 0. Okay, so that is a limit in a nutshell. And if you think about it, even if I would multiply by 2/3 or 3/4, I'm still getting smaller, right? That's depreciating. 3/4 is 75%. I'm losing 25%. 2/3, I'm losing 33%, right? So if I'm losing values, I'm going to be heading to 0. And we'll get to that in a minute there a little bit. There's also some interesting limits. Let's take this one here, for example, the limit as n approaches infinity of 10 times -1/2 to the nth. Oddly enough, that is also 0, but it's 0 in a different way. So again, let's look at our graph, x and y. And when I plug a 1 in, I'm going to have 10 times -1/2 to the 1. Well, that's going to be -5. Plug a 2 in, now I'm squaring it, so that's going to be a +1/4. And then positive 1/4 times 10, so 5/2. And then I'm at -5/4, +5/8, -5/16, +5/32, -5/64. This graph zigzags, it oscillates. It oscillates back and forth, jumping over and over 0. But notice every time we make a jump, we're getting closer to 0. The distance from the x-axis, the distance from y equals 0, is smaller and smaller and smaller. So this is also 0 for that reason, because it converges on 0, much like this one converged on 0. Okay, let's take one more quick peek here. Let's do the limit as n approaches infinity of 10 times 2 to the n. So our first term will be 10 times 2, will be 20. Our second term will be 10 times 4, which is 40. 10 times 2 cubed, so 80. 160. Now this one, hopefully you notice, is growing exponentially. This is not converging on a single value. This is going on and on and on for infinity. It is going to grow without bound. Grow without bound. Unlike the other two examples which converged, this one diverges. Okay, it does not go towards a single value. Okay, it diverges. It's just moving away and away and away. Infinity, remember, is not a value. Okay, so it is heading towards positive infinity, which for the purpose of this course is not really that important. But if you move on to calculus, that is a huge concept in calculus. We're going to focus more on what we just did on the previous page, which we said, hopefully you remember, converges. So let me throw that in here. Converges. Okay, and think about it. Anytime that our multiplier, right, our ratio, anytime our ratio is less than 1, the absolute value is less than 1, so like 3/4, 2/3, negative 1/2, positive 1/2, we're going to get smaller and smaller and smaller, which means we're going to head towards 0 or towards some finite number. Okay, so when the absolute value of the ratio is less than 1, when absolute value of r is less than 1, then the limit as n approaches infinity of r to the n will equal 0, because this guy right here is making things smaller, whether it's cut in half or whatever. 2/3, 1/3, negative 2/3. It's getting smaller. The next little concept here, besides converging and diverging, deals with limits when you're talking about polynomials. So the limit as n approaches infinity. And let's just take a boring n squared minus 4 over 3n, we'll say squared, plus 2n. All right, so you have a quadratic over a quadratic. Now, if you start plugging numbers in, you're just going to get values. You're going to get, so let's plug a 1 in here. We get negative 4. So when n equals 1, we get negative 3, right? 1 minus 4, over 3 plus 2. When n equals 2, we're going to get 0. When n equals 3, we're going to get 9 minus 4, so 5, over 9, 18 plus 6, over 24. Okay, so this guy's here at negative 3/5. Now we're at almost 1/5. Let's just do one more value here. 4, we get 12 over 48 plus 8 is 56, which reduces to 6 over 28, or 3 over 14. Okay, and that's getting to where we're heading here. Bottom line, when you see these guys, the degree in the numerator and the degree in the denominator, the highest degrees are equal, we're going to take the ratio of the lead coefficients. This actually equals 1/3. And let me show you here on a calculator. Excuse me. So let's look at the decimal values. 3/5 is negative 0.600. 5 over 24, 0.2088. 3 over 14, 0.21. Okay, and let's put in like a 10. So 96 divided by 320.3. Let's take 100. 100 squared, right, is going to be 10,000 minus 4 equals divided by, so 100 squared again is 10,000, so that's 30,000. 30,000 plus 200, 30,200.33. We're getting closer to a third. Okay, and the reason this works is a neat little math trick, if you will. I'm going to multiply by a fancy form of 1. And that fancy form of 1 is 1 over n squared times, 1 over n squared divided by 1 over n squared. Look what happens to my numerator. N squared times that is 1, and this is 4 over n squared. My denominator becomes 3 plus 2 over n squared. And you might think that doesn't make it any easier. But remember what's happening to n. This is the limit as n approaches infinity. Well, what's 4 over an incredibly large number? It's as good as nothing. What's 2 over an incredibly large number? That's as good as nothing. So these two pieces become obsolete, minuscule, irrelevant, so that our main focus is right here. Okay, so degree in the numerator equals degree in denominator. Then our limit as n approaches infinity goes to the ratio of the lead coefficients. Again, not a huge concept that we're going to talk about in here, but again, for those moving on to calculus, whether it's in college or as a senior, this is a huge concept. Okay, and there's other pieces to this too. Let's say we have the degree in the numerator is greater than the degree in the denominator. Then our limit is infinity. And if the degree in the numerator is less than the degree in the denominator, we move on to 0. Okay, and these are for the exact same reasons. Imagine if this is an n cubed, so the degree in the numerator is greater than, then I'm going to get n over 3. Infinity over 3 is infinity, and vice versa. If this was cubed and that was still squared, I'd have 1 over n, and 1 over infinity would be 0. So those are limits, kind of a very broad, basic idea there. The idea is that you can follow a pattern of numbers and kind of get an idea of where it's going. Or take an equation and plug some numbers in to find out where it's going. In the case where you're dealing with some polynomials, just to recognize the degree in the numerator and the degree in the denominator. And when I say degree, we're talking about the largest degree. These are both quadratic functions, even though this also has a degree 1 down here as well. All right, so the main focus is there, obviously, is what is a limit? It's where the function is going, if it could actually get there, right? As n approaches whatever it's meant to approach, where's your actual function going? Converging, are you heading towards one value or not? Diverging, is it heading towards one value or not? And that would be the not, right? It would be diverging then. Okay, and again, remember, the absolute value of the ratio is less than 1. That means you are going to converge. That is important for down the road here. Hope you had a good one. We'll chat later.